Hi everyone, my name is Louis Tremblay Thibault. I do cryptography research at Zama, and I'm also a PhD student at the École de Technologie Supérieure in Montreal. The work I'm going to be presenting today is a joint work with my colleague at Zama, Michael Walter, that has appeared at CCS earlier this year, in which we demonstrate for the first time the practicality of a verifiable FHE. So what is verifiable fully homomorphic encryption, or VFHE in short? Well, it's the natural combination of two cryptographic primitives, namely fully homomorphic encryption, or FHE in short, and verifiable computation, or VC. On the one hand, as I'm sure you all already know by now, FHE enables the privacy-preserving delegation of computation. However, FHE by itself does not give any sort of integrity guarantee over the computation that has been performed homomorphically. Okay, and this can cause issues in more permissive adversarial models. So FHE, as we know it, is only known to be secure in passive adversarial models. On the other hand, verifiable computation, or VC, as the name implies, enables verifiable outsourcing of computation. So for example, a prover can convince a verifier that some function f applied to some input x truly yields some output y. However, in order to do so, the prover has to know the function f and the input x, and therefore the output y also. So if the function and the input are to be chosen by the client, then VC by itself does not provide any privacy guarantee. So as I said, VFHE is the natural combination of both. So it enables privacy-preserving and verifiable outsourcing of computation. And if you think about it, that's sort of like the ideal functionality of compute delegation, right? If I, as a client, want to ask some server to do some work for me regarding some potentially sensitive data of mine, I'd like for the server to do this computation blindly over my sensitive data. And I'd also like to receive some sort of certificate or proof that it has executed the computation that I asked it to do. Furthermore, VFHE allows the deployment of FHE in fully malicious settings. And now we're going to dive a bit deeper into this last point, and we'll see what happens to FHE as we know it when we place it into a malicious setting. Okay, so we're just considering the very simple example of a compute delegation. So on the left side, you have the client, and on the right side, you have the server, which we're going to assume is malicious. So the client starts out by encrypting two values. Here, for the sake of the example, we're just going to pick 1 and 2, which he encrypts to the ciphertext C1 and C2, respectively. The client then picks a function. In this case, we're going to stay simple. It just picks the addition function. Then it sends over the function f, or a descriptor of the function f, C1 and C2 to the server, and asks the server to homomorphically evaluate f over C1 and C2. Now, if the server were to be honest, it would simply do the request as asked and simply return the result, and everything would be fine. But now we're assuming the server is malicious, and let's see what happens here. So in our case, the server partially ignores the request of the client, and instead of computing C as f applied over C1 and C2, it instead chooses to encrypt a new ciphertext, which we'll call C star, which simply encrypts some plaintext value that the server has picked at random. Okay, in this case, let's assume he encrypts 2. Then the malicious server proceeds to apply f over C1 and C star. So it replaces C2 from the request with this new ciphertext C star and returns the resulting ciphertext to the client. Now, the client decrypts the result, and since it's the expected result, it's the result of the computation that it expected, it simply proceeds. Okay, maybe it proceeds to terminate the protocol session as normal and basically implicitly tells the server that no error occurred. And what the server can guess from this is that since f applied to C1 and C2 is sort of equal under decryption to F applied to C1 and C star, this implies that C2 is equal under decryption to C star. Okay, so it sort of guessed the correct secret data of the client. Now, admittedly, this was a bit of a lucky shot on the server side, since it guessed the very data that the client used to encrypt C2. But we can see that the server can still learn some information if it picks at random some other data than the one that the client used. So here, for example, it chooses to encrypt 3 instead of 2, okay, and proceeds in the same way. So it computes C as F applied to C1 at C star and sends the resulting ciphertext C over to the client. Now the client decrypts that value C and sees that it gives an unexpected result. Okay, and from this, it raises an error, or it raises a flag from which the malicious server can guess that C star does not encrypt the same value as C2. So whether the server makes the correct guess or not regarding the value to encrypt, these two examples show that the server actually learns something about the client's private information. Now, it's fair to doubt this motivation for VFHE, since these examples crucially rely on the server obtaining some reaction from the client in order to learn some information about its secret data. However, these reaction attacks have been studied for a long time now, and they can be mounted in real-world scenarios. So, for example, you can think of the case where the unexpected result sent back from the malicious server makes it so that the decryption on the client side looks like gibberish, right? The client can't make sense of what it decrypts. In this case, a client could manually resend the same request over to the server, maybe thinking that something went wrong during communication. And so yeah, it would just resend the same request over in the hopes that maybe whatever happened during communication doesn't happen this time around. Okay, so by sending these same requests, the server can sort of guess that there was an error or that the result was unexpected on the client side. You can even imagine some software implementing some retry logic if the software can't make sense of the decrypted result. Okay, so the takeaway from these examples is that there's a risk of the malicious server learning information about the client's secret data whenever the client's behavior diverges from the point of view of the server, depending on whether or not the computation result was the expected one. Okay, so this is basically why FHE, as we know it, is only secure in the passive model, which we also call the semi-honest or honest but curious model. So in this model, the server is always assumed to follow the protocol as prescribed. So it's not allowed to deviate from the protocol and therefore gain information about the client's secret. Now let's see how verifiable FHE fixes this. So verifiable FHE, what it does is it basically adds a layer of integrity to FHE. So what we're doing here is we're sort of forcing a malicious server to behave honestly. So not only will the server, in this case, compute C as the function of C1 and C2, it will also compute a proof that we call pi that attests to the fact that F applied to C1 and C2 yields C. Okay, it's going to send this proof with the resulting ciphertext over to the client, and the client, in turn, will first decrypt, will first verify the proof, sorry, with respect to F, C1, C2, C, and pi. And only if the verification passes will the client decrypt the ciphertext. Okay, so it's important to note here that the client's behavior, so yeah, let me add that if verification passes, it will decrypt the ciphertext and proceed with the rest of the protocol. But if verification fails, the client will instantly abort the protocol. So what we can notice here is that the client's behavior now doesn't diverge as a function of whether the resulting ciphertext encrypts the expected plaintext or not. It now only diverges in function of whether verification passes or not. But the malicious server already knows whether verification will pass or not, because due to the completeness property of the proof system, if the server computed F and C honestly, then it knows that verification on the client side will always pass. On the contrary, if it behaved dishonestly and computes some other proof here, it knows that the verification on the client side will fail with overwhelming probability. Okay, so this is the intuition of why verifiable fully homomorphic encryption is helpful to deploy FHE in malicious settings. So a bit more formally, the result that we get in our work is a security proof in the universal composability model against active adversaries. And the proof is for a protocol, just like the one we discussed. So basically, secure computation delegation using symmetric FHE. The setting in which we position ourselves into is a bit important. So we assume that the client knows the function f and the input ciphertexts C1 and C2 in my example. The ciphertexts are also guaranteed to be well-formed. Okay, this is very important. And as I said, it's very important also that the client verifies the proof first and then proceeds on to the rest of the protocol. Now, this is all very cute, but building VFHE is easier said than done. This is because both of the cryptographic primitives underlying VFHE incur some significant overhead. Now we're moving over to SNARKs. SNARKs is the tool we're using as a means of obtaining verifiable computation in this work. Okay, so we're going to talk about SNARKs from now on for verifiable computation. So the challenges of VFHE are twofold. So first of all, on the FHE side, FHE schemes incur some ciphertext expansion, meaning that the encrypted data is much larger than the data they encrypt. Also, FHE ciphertexts have to include some random noise in order to maintain security, and this noise grows as homomorphic computation is executed. This means that modern FHE schemes have to use some ciphertext or noise management operation, which we call bootstrapping, which is generally the most costly and crucial part of any FHE scheme. Also, FHE schemes make heavy use of arithmetic over cyclotomic rings of this form. And finally, also make use of non-arithmetic operations, such as a module switch. Those two last points are hard to pair with SNARKs, which are usually defined as arithmetic circuits over fields. So basically just circuits with multiplication and addition gates, where the input and outputs are field elements. Moreover, SNARKs are very costly for large computations, especially on the prover time and memory consumption. And as I said, they're usually defined over fields, which makes it quite hard to express arithmetic, ring arithmetic using only vectors of field elements. And furthermore, as you can imagine, since SNARKs are defined using arithmetic circuits over fields, it's quite hard to express non-arithmetic operations using just addition and multiplication gates over fields. Prior work has tackled verifiable homomorphic encryption without considering the bootstrapping. We, in this work, take a complementary approach and only consider the bootstrapping. So in this work, we only generate proofs of correct execution of the bootstrapping, which, as I said, is the most crucial part of any modern FHE scheme, and also the most costly part. Now that we've seen the challenges of VFHE, let's see how we can circumvent them using by carefully picking a FHE scheme and a SNARK. So for the FHE scheme, we choose to go with TFHE because it offers reasonable ciphertext expansion and also has the cheapest known bootstrapping of all modern FHE schemes. Furthermore, TFHE offers a flexible parametrization of the ciphertext modulus, which is going to come in handy later on. Also, Here on the right side, there's a depiction of the bootstrapping computation, and I'd like for you to notice that it basically has a structure of a long loop, okay, where at each iteration of the loop, we compute this, what we call homomorphic CMUX. I'm not going to go into the details here, but the fact that the computation has the structure of a loop is going to be helpful later on. On the SNARK side, we choose to go for plonky2, which is a recursion-optimized SNARK, meaning that it's quite efficient at proving the correct execution of its own verifier circuit. Furthermore, plonky2 is based on the Plonk IOP and the Frye polynomial commitment scheme, meaning that it's quite efficient in practice, since these two technologies are quite efficient in practice as well. The fact that it relies on Frye for the PCS means that it is transparent and publicly verifiable, which unlocks several applications. And lastly, plonky2 uses a small prime field, the modulus of which has width approximately 64 bits, which is perfect for TFHE. So we're going to be able to match the TFHE ciphertext modulus with the prime of the plonky2 prime field. This is going to avoid us having to do modular arithmetic emulation in the finite field, or in the arithmetic circuit over the finite field, which would have caused some significant overhead. So now that we have a FHE scheme and a SNARK, let's see how we can actually build the FHE. So one idea would be to take the bootstrapping computation, the big loop that I was talking about earlier, and simply unroll it, express it as an arithmetic circuit over the SNARK field, and feed that to the SNARK prover. Now, we tried doing this, but the sheer size of the bootstrapping computation would make it so the prover, the processes executing the prover on very big AWS machines would actually run out of memory after having consumed nearly 1 terabyte of RAM. Okay, so this approach is clearly intractable. There's a bit of a wiser approach that we took in order to achieve our goal of proving the correct execution of the bootstrapping, and it relies crucially on this technique called incrementally verifiable computation, or IVC. So we leverage IVC in conjunction of the structure of the bootstrapping. And IVC basically is a technique for efficiently proving the correct execution of consecutive applications of some function. So IVC yields itself quite well to scenarios like this one, where we're trying to prove the correct execution of some computation that has the structure of a big loop, because this big loop can be seen as a series of consecutive applications of the same function. Okay, in this case, the homomorphic CMUX, as I said earlier. So the key idea of IVC is that given this step function, which we'll call f, we build an augmented function, which we call f prime, comprised of the original function f, as well as what we call v. Okay, v here is the verifier function for verifying proofs attesting to the correct execution of this augmented function, f prime. Then at each iteration, each iteration in the loop, I mean, the IVC prover is given the current input, xi, to the function, f, the base input, x0, so the input at the beginning of the loop, as well as a proof that the augmented function f prime applied I times over x0 equals xi. Okay. Now, the IVC prover proves that this augmented function f prime, given these inputs, well, applied one time over these inputs, truly yields the output xi plus 1, okay, which is the loop value at the next iteration of the loop. This proof that f prime truly yields xi plus 1 by recursion actually is a proof that f prime applied I plus 1 times over x0 yields xi plus 1. Okay, this is true because in the proof we've proven that we've correctly executed the verifier, okay, that successfully verified and proved for the previous iteration. So I realize that this is a bit subtle and takes some time to wrap one's head around. But the key point here is that IVC sort of allows to compress a n iteration proof into a proof for a single iteration, plus some overhead related to the size of the verifier circuit. Now, as I said, plonky2 is very efficient at proving the correct execution of its own verifier circuit. So despite the picture here, V is much smaller than F, okay, in our case. So the IVC overhead is quite minimal in our prototype. Now, using IVC, the prover work is still tied to the number of iterations in the loop, because the prover has to perform one proof per step. However, the memory consumption of the prover is much lower, because it only has to consider the circuit for one step, so one F and one V, instead of the circuit for this whole computation here, which is essentially 800 times this homomorphic CMOX, on the order of 800. On the other hand, though, the proof size and the verifier time are only tied now. Verifier time are only tied now to the size of F prime, which is one of the biggest advantages in the IVC. Now, using this methodology, these are the results that we arrived to. So using these parameters in the table at top, which allow for a plain text space of size 16 and allow us to claim 128 bits of security, we're able to prove the correct execution of a TFHE bootstrapping in less than 20 minutes. And we have a verifier time that takes less than 10 seconds on the same machine and can be brought down to less than 5 seconds on commodity hardware, which is less than the time it takes to perform a bootstrapping. By the way, we also tried using ZK-VMs to reach a similar result. ZK-VMs are these tools that basically take in a compiled program, a program compiled in RISC-V usually, and prove the correct execution of that program by proving the correct execution of a virtual machine executing that program. So as you can imagine, this yields a significant overhead. And macro benchmarks indicate that this actually causes about 80 times overhead. Okay, so we weren't able to prove a full bootstrapping, but only one step of the bootstrapping showed that it was taking about 80 times more, 80 times longer than using this methodology. Now we realize that these timings can be a bit hindering for some applications, but we do feel like other applications can make use of this technology as of today. So one example that I have in mind is privacy-preserving hybrid blockchain rollups. So very quickly now, rollups are scaling solutions for blockchains where a layer 2 chain batches or rolls up batches of transactions to the layer 1. Okay. The fact that they're hybrid only means that this work, which is done by a single party, is assumed to be true in an optimistic way. If an observer of the protocol sees that this rollup operator has done some fraudulent work, it can trigger an alert. Okay, and in this case, there's a dispute resolution mechanism, which typically ends with the rollup operator having to prove that his alleged fraudulent work was done honestly. And typically, this rollup operator has a window of approximately 7 days to provide the proof that his work was honest. And we feel like this 7 days window is more than enough time to prove the correct execution of FHE computation. Another fun application that we played with is related to privacy-preserving AI inference. So what we were able to achieve here is we modified our protocol to be able to prove the correct execution of a neuron activation function of the following form. So it's basically a ReLU over a weighted sum of ciphertexts. So the way we do this is that we modify our prototype to receive as input several ciphertexts as well as several weights. And since the bootstrapping computation, the big loop I was talking about, only considers one component of each ciphertext per step, It's able to do what I call a just-in-time weighted sum. So each ciphertext component is multiplied with its respective weight and added together with the other weighted ciphertext components once per step in the bootstrapping. We can replace the identity lookup table by the ReLU lookup table for free in our prototype, which allows us to prove the correct execution of a neuron activation function over ciphertext. So that's it for me. Thank you for your time. Here are the information regarding the paper and the implementation, and I'll be happy to take questions now.